Alright, with question 7, it's a proof, so you're going to have to set out like a proof. So starting with required to prove. This is a statement, of course, of what you're trying to prove. So just simply prove that a complex number multiplied by its conjugate will equal the modulus of that complex number squared. So now, actually performing the proof, you're going to have to define your complex numbers first. So, a complex number, let's say equal a plus bi, because you've got to do a proof in a general sense. And from there, you could then obviously state that the conjugate is a subtract the imaginary part, so subtracting bi. Then start with your left-hand side, and hopefully show the left-hand side equals the right-hand side. So left-hand side equals, show every step in your proof, starting with the left-hand side, the statement, substituting in, and then expand. I'm going to use the FOIL method, so first subtract outer, inner, and last subtract. Just be careful here. Make sure that you square the I as well as the B. Be careful with your negatives. You could have recognised that was the difference of two squares pattern if you wanted to, and just simply made it a squared subtract bi squared. Alright, again, be careful here. If you're subtracting bi, which are both being squared, that means you're subtracting b, but you're also subtracting I squared. Now, I squared is -1, so that means you're plussing b squared. So just be careful with your negatives there. On the right-hand side, okay, if we go back up, that was our right-hand side. So the modulus of z is going to be the square root of a squared plus b squared. So just be careful there not to, when working out the modulus of the complex number, don't take in I. That will cause all kinds of problems. You just deal with the real part, which is a, and the imaginary part, which is b, when applying Pythagoras' theory. So the square and the square root cancel out, so you're left with a squared plus b squared. Luckily that equals the left-hand side, so then you can just say QED, which means quite extraordinary Damien. Thank you very much.